Hey guys, welcome back. Today we get to see why dynamics is so awesome. So we're talking impact. This is what I'm calling an impact and energy example. And it is a problem that contains many of the aspects of dynamics that we have learned throughout chapter 13. So let's take a look at it. In this example, we're given block A, 15 kilograms. It is moving to the left at 10 meters per second. It is subjected to a friction coefficient of 0.3. It's going to slide 4 meters and impact block B, which is steady and attached to a spring. Block B is 10 kilograms. It is attached to a spring that has a coefficient of 1,000 newtons per meter. And we're asked to find the maximum compression of the spring. We are given that the coefficient of restitution is 0.6. So in big picture terms, what we need to do is start from the starting position and work our way to the spring compression. And what that means is that we're given that our initial velocity is 10 meters per second, but since friction is going to be slowing us down, we know that we're going to slow down along this path, and then we're going to make impact, and so we'll calculate the incoming and outgoing velocities of the blocks. Now we'll convert the V, what is this going to be? It's going to be VB prime. We'll convert that to kinetic energy, and we'll do an energy balance between the kinetic energy of the block and the potential energy of the spring. And from there, we should be able to get the max compression. So good place to start is always with the free body diagram. Let's see, are we able to see this marker? Here we go. Okay, so this is N here. And this will be what our mg, our friction force, is opposing the direction of travel. We define the direction of travel as the positive direction. So F is going to be minus mu k mg, right? Friction is fun, N is mg. So mg, and we need a way to relate the friction and distance to our velocity. Well, we can use work and energy from, let's see, that was work and momentum, right? Work and energy. So we use this relation here. Work is force times distance. This is force, so we need distance. And what's our equation look like? It's going to look like U from 1 to 2 is equal to T2 minus T1, right? And I like to start symbolically so that when we can cancel things, we do. So mu k mgs is going to be equal to 1/2 m, and then what? 2 and 1. Let's do this. Let's call this 1 and this 0. That means that this will be a work done from 0 to 1 because I've already numbered the positions. And so that would be V1 squared, which is what we're after. And it's going to be minus V naught squared. Right, so the masses cancel, and we are solving for V1. So we'll multiply, this is minus, that's negative. So we'll multiply this times 2, and then let's plug some numbers in here. We get minus, well, now we can, this is just as easy to do either way. So times 2 plus V naught squared. So V naught squared minus 2 mu k g s it's going to be equal to V1 squared. Okay, and then we'll take the square root. So V1 is going to be equal to the square root of V naught squared is 100 minus 2 times 0.3 times 9.81 times 4. And that's going to be equal to, I should really get out of the habit of doing that. It's not as pretty. Let's see. V1. And I'm sorry, I was talking about continuing these, making these lines long. Let's see, this is 8.7439 meters per second. Okay. All right, cool. So that's step one. And that has taken us from 0.0 to 0.1. We started at 10 meters per second. Friction slowed us down to 8 point, looks like a little bit less than 8 3/4. Okay, so the second part is the impact. And we know from the previous examples that we're going to need two relations. So let's see, MA VA prime plus MB VB prime is going to be equal to MA VA plus MB VB, right? And VB is 0. Okay, so let's see, the mass is 15. 15 VA prime plus 10 VB prime is equal to 15, and VA is this guy here. So before we do that though, let's reduce these. So this will be VA still, but we can reduce these. This is, we divide everything by 5, this becomes a 2, this becomes a 3, and this term becomes 3 times this guy here. So 3 times 8.73, or excuse me, 7439. So that times 3. And that's going to be equal to 26.2317 meters per second. Okay, and similarly, we can do the same thing with this equation. So V prime A, let me circle this, we'll call this 1. VA minus V prime B is equal to E times, and we can just use the value, right? 0.6. And that is going to be VB, which is 0, minus VA, which is 8.7439. And if we solve this for VA, we can substitute this into equation 1. So VA prime is going to equal VB prime, and that'll be minus 0.6 times 8.7439. So 0.6 times 8.7439 is 5.2463. And we'll call this equation 2. All right, so we'll substitute equation 2 into equation 1. It's always good to leave yourself a note about what you're doing. And dividing your sections is also not a bad idea. So we get 3 times VA is this, so 3 times VB prime minus 5.2463 463 plus 2 times v prime b equals 26.1317. Okay, so then that is 3 times VB prime minus, so times 3 is, so it's going to be minus 15.739 plus 2 times VB prime is equal to 26.1317. So we'll add 15.739 to both sides. And plus 317. So that gives us 41.8707. And 3 VB prime plus 2 VB prime is 5 VB prime. We're solving for VB prime. V prime. And so we'll divide both sides by 5. So VB prime is going to be equal to that divided by 5, which gives us 8.3741 meters per second, right? So this is what we need to remember to, so A has come in, we have made contact. We can calculate block A, but really we're interested in block B. So we need this. And now what we need to do is convert the energies, right? So the energy right here, we'll say that E is, well, actually it's easier to do this, right? So we'll just say T, and let's call this position 1, and the compressed part we'll call position 2. So we'll say T1 plus V1 equals T2 plus V2, right? So this is the kinetic energy, and V is the potential energy of the spring, right? So when this is before compression, this is once it's compressed. So before compression, let's write these out. We'll say 1/2 m, and we'll say B, V squared, V1 squared plus 1/2 K x 1 squared equals 1/2 MB V2 squared plus 1/2 KX squared. And at the most compressed position, this is X max, right? This is what we're trying to solve for. Well, by inspection, we know that the spring is not compressed, so X1 is 0, right? And when the spring is at its maximum, then all of the kinetic energy has transferred into the spring and things are no longer moving. So there is no velocity. And so what we get is 1/2, and I'm going to use m here because we're only left with b. So 1/2 of 10, and our velocity, this guy here, so 8.3741 squared. It's going to be equal to 1/2 of k is 1,000, and x max squared. Okay, so these cancel. This becomes, we divide 10 from both sides. Well, we can just divide 1,000 from both sides, right? And so this becomes over 1,000, goes to 1. So then x max is the square root of this, Right, so we can take the root of that. So let's see, 10 square root of 10 times 8.3741 squared divided by 1,000 is 0.8374. And that's going to be in meters. Wow, that is a long way. If you think about it, that is 837 millimeters. That's quite a ways, right? A meter is 3 feet, so we are more than 2/3. So that is more than 2 feet. So at any rate, the bigger picture with these is you just work from where the action is to the end of the problem. And I think it's super fun. I am looking forward to more creative and fun examples. And I hope you liked it, and I will see you in the next video.